In an earlier ACT video, we took a look at adding and subtracting expressions with radicals. And in this video, we're going to finish that up by multiplying and dividing expressions with radicals. All right, so with adding and subtracting, you had to have like terms, which meant the radicals had to be the same. When you're multiplying, just like when you're multiplying expressions with letters, they don't have to be like terms. For example, what you're used to seeing with letters is maybe 3x squared times 4x cubed. And when you multiplied these together, they weren't like terms because this x was squared and this x was cubed, but that wasn't a problem. You multiplied the coefficients, 3 times 4 gave us 12, and you multiplied the x's, and the bases were the same, so you add the exponents, giving us x to the fifth. So they don't have to be like terms. Likewise, when we're multiplying expressions with radicals, they don't have to be like terms either. What you're going to do is you're just going to multiply the numbers that are underneath the radical. So this is the same thing as the square root of 10 times 15. You can put it all under one radical, but we typically don't do that, but this is what you're actually doing. Then when you multiply 10 times 15, that gives you the square root of 150. But just as we've seen in prior videos, we can't leave a big number like that. We will always want to simplify. So we're going to go to the margin, and we are going to find the biggest perfect square factor of 150. And when you go through your factors of 150, you find that it's the same thing as the square root of 6 times the square root of 25. And if you remember your divisibility rules, 150 ends in 0, so it may make you think about multiples of 5 and 10. All right, this works out great because the square root of 25 is a perfect square. It's 5, and you bring down the 6, the square root of 6. Now, you know this is completely simplified because that number 6 right there has factors of 1 and 6 and 2 and 3. None of those factors are perfect squares, so that means you're done. Now, when you're dividing, it's a little bit more work. Right here we see we have the square root of 72 divided by the square root of 9. Well, just like when I was multiplying, I could put both numbers underneath one radical. We can do the same thing when dividing. And it would be to our advantage to do that in this problem because we would end up with the square root of 72 over 9, which works out well because 72 is divisible by 9. And 72 divided by 9 is 8. So this leaves us with the square root of 8. So you can divide the radicals, or you can rewrite it where they're under one radical and then divide. But we can't leave the square root of 8. We need to go ahead and simplify that. We know that simplifies to two factors, square root of 2 times square root of 4. 4 is our perfect square. The square root of 4 is 2. Bring down the square root of 2. 2 square roots of 2. The square root of 8 pops up so much that you probably end up memorizing it as 2 square roots of 2. All right, what if it doesn't divide evenly? What if we have the square root of 3 over the square root of 39? Well, what happens here is you can rewrite this as the square root of 3 over 39. And we can simplify this fraction, and this gives us the square root of 1 over 13. Now, we typically don't leave fractions under a radical, so I'd actually go back to writing it where it's split up. Square root of 1 over square root of 13. You may consider skipping this step, but this is essentially what's happening. Well, we got lots of simplifying to do here because in the numerator, the square root of 1 is 1. So I'm left with the square root of 1 over the square root of 13. The issue with this is we don't typically leave a radical in the denominator. So we have to do something called rationalize the denominator. That means get the radical out from the bottom. So let's take 1 over the square root of 13, and we're going to rationalize that. We got to get that radical out from underneath the bottom of the fraction. So we're going to multiply this by the number 1, but it's not going to be the number 1. It's going to be the square root of 13 over the square root of 13. So anything over itself is equivalent to 1. So we are multiplying it by 1, we're just writing it in a different way. Now we multiply across. 1 times the square root of 13 is just the square root of 13. On the bottom, square root of 13 times the square root of 13 is just 13. The radicals cancel each other out. Why? Because, let's go over here. Why do those radicals cancel each other out? Square root of 13 times square root of 13 is the same thing as the square root of 13 squared. And squaring something and taking the square root of something are inverse operations, so they cancel right out. So we're left with square root of 13 over 13. All right, so let's do one more. Let's take a look at 4 square roots of 2 over 2 square roots of 5. Well, here we have 2 things we need to simplify. The first thing I see we need to simplify is the obvious 4 over 2. So let's go ahead and simplify 4 divided by 2. This is going to give us 4 divided by 2 is 2 square roots of 2 over the square root of 5. Now what I see next is 2 over 5. Nothing there simplifies. That is completely simplified fraction if we were to put it under one radical. What I mean by that is if we were to take and write that as the square root of 2 over 5. Nothing we can do there. We're done with that. So the only thing we have left to do is rationalize that denominator because we don't like that radical down there. So that's the square root of 5, which means we need to multiply this by the square root of 5 over the square root of 5. Well, in the numerator, that's a 1 in front of that radical. So when you multiply 2 times 1, that gives you 2. And when you multiply the square root of 2 times the square root of 5, that gives us the square root of 10. All divided by square root of 5 times square root of 5, plain old 5. So we end up with 2 square roots of 10 over 5. That's completely simplified.